Thank you for joining. My name is Reischke, and I would like to talk about a project I've been doing during the last few months with my collaborators in Heidelberg, Karlsruhe, and Stockholm, which I've listed here, which are Martin Fax, Steffen Hagstotz, Andreas Partner, Björn Malte Schäfer, and Thomas Schwetz. And I would like to talk about Axions as a dark matter candidate and how one can constrain the Axion models with the large-scale structure of the universe. And I would like to divide my talk into 4 parts. I would first like to briefly motivate axions and why they are an interesting dark matter candidate. Then I would like to introduce the production mechanism and the scenario of the axion-like particle we are considering in this work. After that, I will describe the data which has been used to constrain the dark matter model of the axion, especially the cosmic microwave background and its primary anisotropies, as well as Sanayer-Sedovich clusters as obtained by the cosmic microwave background and the CMB lensing signal itself of the lensing of the cosmic microwave background. And then in the last part, I will give a brief summary of what we have found, as well as some outlook on future work and future directions. So let us directly start with why axions or dark matter in general. So dark matter has been around now since a few decades, and there's plenty of evidence that there must be, or there should be, some non-radiating matter which makes up most of the normal gravitating matter in the universe. However, from a particle point of view, nothing has been decisively found so far. And due to this, there exists a whole zoo of possible dark matter candidates, which are, I think, best summarized in this great XKCD comic by Randall Munroe, where you can directly see that this ranges from very, very light particles in the region of electron volts, even smaller. And in the work here, we are talking about masses which are 10 to the minus 20 electron volt, or even lighter, but also up to 10 to the 30 kilograms. So you see that this spans a vast amount of orders of magnitude in mass. So there's a lot of possibilities you have for dark matter candidates, but so far it hasn't been possible to decisively constrain them. So axions in this picture live on the very left, so they're very, very light. And why can they be very light? So the normal problem with dark matter is that if they are thermally produced and they are very, very light, it's very hard or impossible if they are too light to match the correct relic abundance so that you have the correct density of dark matter today. However, when they are not non-thermally produced, they can be very light and still have the correct relic abundance, which we observe today. And on the other hand, if they are also very light, they have a very large de Broglie wavelength, and therefore they could possibly leave imprints in the large-scale structure if they are so light that the de Broglie wavelength is as big, for example, as a galaxy, or slightly smaller, but such that you can see any signal from this effect. So this is why axions are an interesting candidate, because you can directly, in principle, for certain mass ranges, see imprints in the large-scale structure. So how do axions form then in the early universe? And axions were first discussed in the context of the strong CP problem, which arises from quantum chromodynamics. And this strong CP problem was solved by the Peccei-Quinn symmetry breaking. And this works as follows. So you first have a complex scalar field, and then a global U1 symmetry, which is called the Peccei-Quinn symmetry. It's spontaneously broken. So you have the field here in red on this Mexican head potential, and it spontaneously rolls down into this new minimum, like for the Higgs. And then the Axion field is associated with the phase degree of freedom in this hat. So it can assume any value between -pi and pi in this region. Later then, at the QCD phase transition, upon further cooling, the potential of the Axion field is generated. So you have an additional symmetry breaking, and this hat is basically flipped a bit to the side. And therefore, the Axion field starts rolling down this potential and starts oscillating around this minimum. And this essentially gives the Axion its mass. Now, why are there any imprints on the large-scale structure by this effect? So the question now is, does the symmetry breaking happen before or after inflation? The scenario we're considering here is that the symmetry breaking happens after inflation. So then in causally disconnected patches, which we can observe today because they re-enter the horizon after inflation, the field or the Axion field will assume random phases, because in one patch it will roll down like this, in another patch it will roll down like this. Now, if the additional symmetry breaking or the potential of the Axion is now turned on at the QCD phase transition, then what happens is that the field starts from different values or different initial values to roll down its potential, and therefore oscillations are different. Therefore, the energy stored, or the energy density stored in these oscillations is different, which leaves, since all patches are uncorrelated, leaves just a white noise power spectrum on top of the normal fluctuations. And these objects which form there and obey this white noise power spectrum are called Axion mini-clusters. And therefore, you get additional perturbations just by this mechanism because it's after inflation. If you would have it during inflation, you would have the normal spectator field, which would also induce isocurvature perturbations. However, these isocurvature perturbations in that case would follow the same spectral shape as the adiabatic fluctuations. So this is how you generate, in principle, the fluctuations of the Axion field, which you can observe. So the signature we are looking at is the following. So in this plot on the very right, we show just the normal linear matter power spectrum. So we have the wave number on the x-axis and the power spectrum on the y-axis. And we show the normal adiabatic power spectrum for different redshifts, but also the isocurvature component as induced by the Axion for a certain Axion mass. And this brings me basically to the model we assume for the Axion. So one important aspect of the model is how does the Axion mass evolve in the early universe. So it goes from massless to massive, still very light, but it has a mass. And the question is how this transition happens. And this depends strongly on the model. So what we assume is that you just have a power law transition, so that you have a vanishing mass at high temperatures, and then you have a transition at the Peccei-Quinn scale Fa, which is related to this to the lambda here, and then the mass is in the end turned on, which would be Ma, which is the zero temperature mass of the Axion. And the parameters b and n control when this transition exactly happens, whether it happens exactly at the Peccei-Quinn scale or a bit later or earlier, and how fast it will happen. And we then parameterize the fluctuations by the isocurvature to adiabatic fractions of a fraction of the perturbation at a certain pivot scale. And this adiabatic fraction can directly be related to the parameters Ma, b, and n. So, for example, given a fraction of isocurvature perturbations within this model with the white noise spectrum, as we see here, at very high k, then for given b and n, we can directly infer the mass of the axion. That is the idea. And for this, we have to assume that all the dark matter exists in form of this kind of axion. So now to the next part. What kind of observables do we take into account? So first, we are looking at the cosmic microwave background. And what we are doing is we are fitting the normal lambda CDM model. However, we include an additional isocurvature component, which has a fixed spectral index, such that we have this white noise power spectrum, because this is dictated by our model. And we then fit for this isocurvature fraction. And I've written down here the definition of this isocurvature fraction again, and this is given at a pivot scale of 0.05 h times megaparsec to the -1. And what you can see in this plot is if we combine the primary anisotropies plus BAO, or even without BAO, we see that this is consistent with, or actually expects, a non-vanishing isocurvature component in the cosmic microwave background. So if you take this seriously for the moment, you can directly translate this into axion mass bounds, which we plot on the right, which of course depend on the parameters of the mass dependent of the temperature dependence of the mass. And you can see them here. So if you have if the transition from massless to massive is very shallow, then you see that you have this band here, and the axion mass is around 10 to the -20. However, if you go higher to more steeper transitions, then you get different constraints. And this is for these isocurvature component here. Okay, we can now take a step back in the cosmic microwave background, and we can ask ourselves, okay, let's just assume we have an isocurvature component, or we allow for an isocurvature component, but now let's leave the spectral index also free together with the amplitude. And what is interesting is that if you look here, so we have here again in this plot on the y-axis the fraction of isocurvature of the isocurvature component relative to the adiabatic component, and on the x-axis we have the spectral index of the corresponding isocurvature component. And interestingly, the posterior directly peaks at the spectral index we would expect for our model, where you get the white noise power spectrum. However, of course, in this case, it's also that it's not, since we have an additional parameter, it's not so significant as in the plot before, the signal that we have a non-vanishing isocurvature component. So this is somewhat interesting that you prefer in the CMB the kind of axion model we are investigating here. Well, okay, so this is all very nice. However, one shouldn't get too excited about this, because there's a problem with other large-scale structure probes. So now if we, for example, take into account also the galaxy clusters as probed by the CMB through the Zaviaev-Zeldovich effect, the tendency that you have an isocurvature component vanishes. So this is this brownish line here, where we add the BAO, and we have the Zaviaev-Zeldovich clusters as well. And if you combine this with the CMB, you get this purple line here, and you see that the preference of the isocurvature component completely vanishes, basically, which is completely driven by the clusters, as you can see here. So if we now take this theory seriously, we can at least put a lower bound on the mass, because if the mass is smaller, then the isocurvature contribution is higher, and you would see it earlier in the CMB, just because of the nature of the mechanism and the de Broglie wavelength. And therefore, we can put lower limits. So everything below this line, below the orange line is excluded for n equals 0.1. And for example, everything below the red line is excluded for n equals 10 and b varying along this direction. So there's a mass range which is included depending on the Axion model. Okay, so now an additional question is, for example, what happens if we would have, for example, stage 4 data, or if we could include data from Euclid. So we also did a forecast for stage 4 CMB experiment and Euclid-like survey, where we include cosmic shear, galaxy clustering, and CMB lensing. And what we find is that if you include only the linear power spectrum, basically, you get these curves here, the three curves on top, depending on whether you marginalize over the cosmology and over the bias parameter for galaxy clustering, or if you include also the nonlinear power spectrum for, I must stress this, we don't have an exact prediction now, especially for this isocurvature component. So this is just a crude approximation. You would get these constraints for the 1 sigma error on the isocurvature component, and these constraints are of course very, very tight compared to the current constraints. They're tighter by 2 orders of magnitude roughly. But for this, you really need to have an accurate prescription of how to model the nonlinear evolution of the Axion field, or the isocurvature component induced by the Axion field. In order to get rid a bit of the nonlinear evolution of the Axion field, what we did is that we introduced scale cuts. So we only counted multipoles up to a certain maximum multipole, such that we only pick up scales below the nonlinear scale at a given redshift. And for an optimistic survey or optimistic scenario where we assume that we can kind of describe the evolution of the power spectrum induced by the adiabatic and the isocurvature component for a Euclid-like survey, we get these mass bounds, which are roughly 2 or 3 orders of magnitude better than the current mass bounds you would have, which are then competitive with other probes. Okay, so I will now jump to the conclusion. So what have we found? What is the current situations of axions in the post-inflationary scenario? So first of all, I would like to stress that we found a non-vanishing, or that we have seen a non-vanishing white noise isocurvature component in the primary CMB anisotropies, which is like, yeah, it's a 3.1 sigma. I wouldn't call it detection, but 3.1 sigma significance at this moment. And we have then found that the Axion model, which we discuss here, actually fits a real feature, exactly this feature in the first point, in the CMB data. However, only in this primary CMB data alone, and this is not supported by large-scale structure measurements like galaxy clusters. However, even if you don't detect a certain mass range, you can still set upper bounds on the Axion mass. So if you combine CMB galaxy clusters and BAO, you find an Axion mass which is bigger than 10 to the minus 21 or 10 to the minus 17 electron volts, which depends on the details of the model, as you have seen in the other plots. So what is next? So it is very important and key to this investigation, as we have seen in the previous slide, that you have a good understanding of the nonlinear evolution of the Axion mini clusters and how they evolve and induce these additional fluctuations in a cosmological setting. And this is at the moment ongoing study, and at the same time we are working on a comprehensive overview of joint constraints on these axion-like particle masses across different scales and different probes, because, for example, also from satellite galaxies, you have constraints on the axion mass, and you can also put constraints on axion mass from the pre-inflationary scenario, as I mentioned, where you have a spectrometer field, and so on. And therefore, it would be very interesting to combine all these results. Also, for example, include different production channels. So you can, for example, also form these axions via cosmic strings. And this is also ongoing work at the moment. So I will leave you with this slide, and yeah, I hope you enjoyed the talk, and I thank you for your attention.